Okay, let's go ahead and keep going through this various review of our many tests. So we've talked about specific types of series. Now let's talk about some different tests. In this case, we have the comparison test. Now the comparison test is one where we say, well, it's not p-series, it's not harmonic, it's not geometric, but wait a minute, maybe it's kind of harmonic, maybe it's kind of p-series, maybe it's kind of one of these other tests. So what we need to do is we need to determine, can I use something that's similar that allows me to compare two series? So for example, if this is our actual series right here, boo, but we can find another series that's above it that converges, then that means the one that's below the converger must converge. Likewise, if I have a series, actually right here, the series right here that's ours, and it's above one that diverges, then clearly it's going to have to diverge. So if I put them all on one graph, if I have this, anything that's a converge below it will converge. If I have something that diverges, anything above it is going to diverge. The challenge here is the stuff in the middle. What happens in the middle? And we're going to talk about some of that coming up quickly. But from here up is definitely diverge. From here down is converge, because we can compare the real ones to two that we actually do know. So that's the basic idea with the comparison test. So what we do is actually go through and we say, for each of the following series, use the comparison test to determine whether the series converges or diverges. In this particular case, we say, well, wait a minute, 1 over n cubed blah, 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 blah is super duper similar to just 1 over n cubed. Well, n cubed, we know, converges. Okay, and this is definitely going to be smaller, 1 over n cubed plus anything is definitely smaller than 1 over n cubed. So if this converges, guarantee this is going to converge. And that's how you continue to work it through. So you find something that's very similar to say, well, if this converges, then the one that's below it also converges. Okay, so there we go. Next, if we do this comparison, we say, well, fine, what we're going to actually do is find the original function that we have, a sub n. Oh, I'm sorry. So that's comparison test. Now, let's take a look at that area that is in the middle. Okay, so here we go. We got converge. We got stuff that's below it would converge. Yay. We have diverge. We have stuff that's above it, and that's definitely going to diverge. But what about this stuff in the middle? Well, what we could do is we could do what's called a limit comparison test. Because what if I have a series like this? It might be above the converge, but it's like super duper close. So in that case, we can take the limit comparison test. And this limit comparison test is pretty easy. You take your original function and you put it over top of, divide it by the function you're comparing against. Now, in this particular case, this is important because n squared minus 1 is not less than 1 over n squared. It's actually greater than 1 over n squared. Because if it were less than 1 over n squared, we could just use the regular comparison test. But it's actually greater because you're dividing by less. So we stack them up. So I got a sub n on top, b sub n on bottom. We're dividing them up. We're going to take the limit as they approach infinity. Well, it's going to take some simplification and blah, 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 blah. We come up with the limit comparison test. And if that limit comparison test does not equal 0, then they either both converge or diverge. Now, here's the thing. All we've said is if it goes to not 0, then it does something. Okay? It does something. Now, in our particular case, when I put these two together, I'm going to end up with n squared over n squared minus 1. Well, if I take the limit as that goes to infinity, well, the problem is infinity over infinity, L'Hopital. But if I do L'Hopital, down, 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 I come up with equals 1. Well, is 1 not equal to 0? Not equal to 0, so they either both converge or both diverge. Well, here's the deal. If it does equal 0 and one converges, then the other converges. And if it's equal to infinity, then one diverges, guaranteed the other diverges. But in this case, we have a series where it's not equal to 0 and it's not equal to infinity. So there it is. They both converge or diverge. But wait a minute. What did we say this one always is going to do? Converge. Okay, so if this is always going to converge, then automatically that converges. That is the short version of the limit comparison test. All right, with that, I'm going to end this video and we're going to pick it up next time.